Just going to hand it off to Alexa, but first I want to just introduce Alexa to you all. So again, Alexa Fredston is a postdoctoral associate at the Pinksy Lab in Rutgers, or at Rutgers University. So she's joining us from New Jersey today. Her research is focused on the ecological processes and the biogeographical patterns in the context of human impacts. And her focus areas do include species biogeography and climate change. So looking at processes that drive species movement and distribution with regard to climate change and climate impacts. She also does research on sustainable fisheries and livelihoods and looking at how fisheries can provide protein to address our emissions and climate emissions. And then she's done a lot of research also on coastal ecosystem and runoff dynamics. Looking at the value of marine ecosystems in supporting biodiversity and natural services. And what's really cool is that all of this work is done in R. So with that, Alexa, I'm gonna hand it off to you, and we're really looking forward to hearing how you do this work. So I guess I have to stop sharing screens. All right. Do I stop sharing? Great. Your turn. Thank you so much.
Thank you for having me, and hello everyone. I'm really impressed that you've all chosen to do this at the end of your workday. For me, it's the middle of the day, it's lunchtime, so it's a much easier time of day, I think, to get excited about coding. But hopefully this will still feel exciting, and I was glad to see not all of you wrote that you're totally exhausted in the chat, so thank you for that energy level. What I'm sharing right now, which I think you can see, is just a browser window looking at the GitHub page for this repository. So many of you are probably familiar with GitHub. And if you're not, we'll just say that it's at the moment where all of the code for this presentation and this demo is stored. I wrote the slides in R in addition to the demo, so we can actually access them from here. And if you get lost at any point or want to follow along with the slides, I think that they're also in the organization repo, but you can find them here, A Fredston, R for the Planet, and they're also here. I titled this talk R for the Planet because I think it really captures what I wanted to accomplish talking to you today, which is to think about how those of us who work on issues related to the planet, I'm going to call us environmental data scientists throughout this talk, but it's geographers, it's statisticians, modelers, social scientists, and a broad array of researchers and practitioners, how we use R to further our work goals. We all live on the planet. You're here. It's underneath you if you look down. But humans have had a lot of impacts on the planet that are what I focus on trying to understand and in many cases adapt to or mitigate. The biggest impact that we often talk about and hear about in the modern era is pollution associated with human activities and human industry, and predominantly pollution in the form of gases emitted by the combustion of fossil fuels that move up to our atmosphere and trap heat. They act like a heat trapping blanket wrapped around the Earth that make the surface of the Earth, where we are down here, a little bit warmer. It's not actually what you might think in terms of weather, that much warmer, but in terms of our global climate system, it causes a lot of very large scale changes. But there are many other ways that humans have transformed the planet. Of course, lots of other forms of pollution that aren't greenhouse gases. A big one that I think about a lot is the way that we've transformed nature or wild habitat. Humans have transformed something like half of the land surface on Earth into something that is not what it was before in our short time as a species on this planet. That often involves cutting down forests to create agricultural lands, not just for farming food, but often for raising livestock. And it also comes in the form of clearing wetlands or mangroves for coastal development, or getting rid of grasslands, and lots of other historic habitats. So to summarize, human impacts on the planet, they are real. They're not good for the planet or for people because so much of our health hinges on having healthy air, clean water, healthy food, and other resources provided to us by the planet. It's definitely us, and I'm happy to talk more about any of these questions later, but there's no other process on Earth that could cause these changes. And it is not too late to act on them, which is another question I very commonly get. In the environmental world, we often say that the best time to act on climate was yesterday, but the second best time is right now. So hopefully this doesn't leave you with a sense of despair, but rather a sense of purpose. And I think that's especially important because there are a series of crises waiting in the wings around the climate crisis, like the biodiversity crisis, that won't be fully resolved by mitigating climate change. So I've put a lot more resources here if anyone's interested in climate specifically, that are really accessible. These are a number of different podcasts, a great YouTube channel, a documentary series from a few years ago that was very well done. And the New York Times just put out an article a few days ago answering frequently asked questions about climate change. So these are all from experts on the climate, and these are also just a handful of the thousands of experts that you can follow on Twitter who I particularly like. It's an ecologist, a climate scientist, another climate scientist who's done a lot of science communication, especially with the faith community, and a political scientist working on climate. So what does all this have to do with R? R has played an enormous role in how my field has progressed in the past few decades. It is really the programming language of choice for ecologists and environmental scientists, especially the open source language of choice. And I think that's for a number of reasons. First of all, it's really good at statistics. I said I was going to call us environmental data scientists, and we do a lot of data science, but we also do a lot of statistics and modeling. And R is at its heart a statistical language that does those things very elegantly. Also, being an open source language, it's very helpful for facilitating transparency and reproducibility, especially in contrast to another language people often use for statistical stuff, which is MATLAB, which is not an open source free language. It's really important in the kind of work I do, in my opinion, to be transparent and to do work that's reproducible. If you're in the climate space, there's a tremendous amount of intentional disinformation circulating about that work. So transparency is particularly important in disseminating results that other people could reproduce themselves from the same data, I think helps to combat that disinformation. But it's not just true in the climate world. People working on endangered species that are important to the public, or working on saving intact pieces of habitat that have cultural value to the communities around them, want to be really transparent about their work. So it blends well with our ethic as environmental scientists to share openly what we're doing and be very clear about what we're doing. And that's facilitated not just by R as a language itself, but by the whole R ecosystem, from our studio to GitHub to R Markdown. And again, if some of those words aren't familiar to you, don't worry, you can ask me about them later, and I'm happy to give you resources to learn about them. But together, this ecosystem enables us to do better science in less time. And this is actually a link to a paper written on this topic by a friend and colleague of mine, demonstrating how much time they saved by using state-of-the-art, tidy techniques for taking in environmental data, wrangling it, analyzing it, and producing an output, which is something all of us who write code for a living need to do, right? If you use any form of data, you need to take in the data, transform it however you need to, analyze it the way you want to, and produce something that you can share. And that process is how we all spend our time. And of course, you want it to be as efficient as possible. And this ecosystem creates great efficiencies in that realm. I also asked this question, why R, for my community of researchers in particular on Twitter, and got a bunch of interesting responses. One person highlighted what I've just been talking about, this analytical workflow from the data to the output. In this case, he says a nice PDF is something that's useful to highlight. And he also mentioned something that I think is really crucial, which is domain expertise. Something that, of course, we worry about, because anyone with expertise in a particular area, I think, would worry about this, is data about the environment being used and interpreted by people who aren't that familiar with where it comes from. And so I'm going to encourage you to explore this type of data anytime you're interested in it, but also to be aware that there might be caveats that aren't evident to you without partnering with someone who's worked in that realm really extensively. A great example is I use a lot of biodiversity survey data, which is when people, usually government agencies, go out into nature every year and in a very standardized way count all of the species that they encounter and how many of them they encounter. If you look at some of those data sets from the United States, it looks like there was a huge dip in biodiversity in 2009. But that's not reflective of what happened in nature. It's reflective of the fact that our government shut down and lost a huge amount of money, and the federal agencies that operate these surveys weren't able to complete them. And so you might misinterpret that without partnering with someone who can say, ignore the 2009 data because that isn't reflecting what you think it is. Another colleague said R is a gateway drug to GIS, which is something else about R that I think is a huge strength. It's really good with spatial data. GIS stands for Geographic Information Systems, and it is the methodology that we use to analyze spatial data on computers. Basically, since the dawn of computers, though, there's kind of been one way people have done this, which is their proprietary software called ArcGIS. It's sort of the Microsoft Word of maps and spatial analysis. It works really well and can do a lot of useful analysis, but because it's proprietary and because it is not based on code, it's much harder to integrate into a reproducible workflow. So R opens up that world to you, which I think is tremendously useful. Other people mentioned mentioned spatial stuff as well. Someone said that the R ecosystem is becoming a net positive, so a useful tool for climate data, which is a particularly gnarly form of data. When I say climate data, I mean global gridded, so they're on a spatial grid, data sets of things like temperature, wind, precipitation, oxygen concentrations. These go back in time a long way, and they also go forward in the future when they've been generated by global climate models. In either case, they tend to be extremely large in size, and partly to ensure that they can still be used with climate models developed in the 1980s or 1990s, the format that they're in tends to be quite clunky. So R has become really good at incorporating those into workflows. And this first person tagged in his tweet someone who's been really involved in the development of software to aid that process and said, has this been 10 years in the making? And the guy said, no, it's been at least 20, and climate science needs R so bad, it's amazing. The last input I got from social media, which I thought was a really touching one, is that R is the cure for the shifting baseline syndrome. This is something that's been described in ecology as a change in what those of us who study nature see as the baseline state, which is important because in order to restore nature, we need to understand what we're restoring it to. We need to have a goal. But if you take a 70-year-old person who's been studying the Great Barrier Reef and ask them what it should look like, they'll give you a different answer than if you ask a 40-year-old who's been studying the Great Barrier Reef, because the 40-year-old never saw it in the state the 70-year-old first saw it in. And this is hard to combat because we don't have data sets that are quantitative and rigorous that go back very far in time. We haven't been surveying nature for that long. But this person pointed out that doing reproducible, standardized analyses of biodiversity change is kind of the only way to combat it, by systematically saying, well, here is where we're starting and here's how much things have changed. So I'm gonna, give you some concrete examples of ways that environmental data scientists have used R. These are all, no, I didn't make any of these, but these are projects that are complete that I've found and I think are great examples of different ways that R has made working on environmental questions easier, better, more transparent, more reproducible. So I'll go through all these just to give you a flavor of what's out there and how people have been using R, and then we'll switch to doing the demo together. If any, these are all completed projects, they're pretty sophisticated, so don't panic if you see the code and nothing in it looks familiar to you, because I'm also going to show you the output to which you could eventually build up with the code that's associated with it. The first one is about environmental health. So it's a spatial project looking at maps, and it's addressing a question that I think is a really critical branch of environmental research, which is how the environment affects human health. And whether there are disparities in that relationship over space, which there, as you'll see, very much are. The environment, you can imagine, affects our health in lots of ways. I've been sneezing for months. That's one way it affects our health. But actually, a lot of that relationship is through air and water, and what human activities have emitted into the air or put into the water that affects our health. And this is a map of air quality versus what is called redlining, which is a nickname, at least in the United States, for when banks or companies, or often the federal government in a housing program, colors an area in red in a neighborhood and says, we won't lend anyone in this neighborhood money to buy a house because we think it's too high risk. So that's often how people who have,
Alexa,
yes. Can you still hear me?
are we supposed to see a screen?
Oh, not yet, sorry.
Oh, okay, yeah. Okay, I just wanted to make sure because I already had you describing it. So, okay, sure.
Yeah,
Sorry about that.
I wanted to just explain this idea first. So what redlining means that someone who would give you a mortgage basically said, we can't give anyone a mortgage in this area on a map because we think it's too high risk and they won't pay back the mortgage. And in the United States, this was used really widely in the 20th century to deny people of color, especially the Black community, mortgages for a home. It's just one of the primary ways to build wealth over generations. So you can go find maps for most cities in the United States where the Black communities are literally shaded in red and no one would give them a loan for anything, especially to buy a house. Those communities have a lot of other inequities associated with them still, and this map was asking whether communities that were redlined 100 years ago still have different environmental health. So the map is going to take a second to load. Oh no, it loaded faster than usual actually. And this was designed by the California Environmental Protection Agency. So there's some more information if you're curious about how it was made, but let's just go look at this map. So this is an interactive app written entirely in R through a package called Shiny, which creates interactive tools that you can interface with on a website. Again, if you haven't heard of it, I'll show you the way that these people made it and you can explore it later. This is showing you Sacramento, but let's pick a different city because I don't know Sacramento. Let's pick Los Angeles. And on the right, what you're seeing is the redlining, or rather how insurance companies and the federal government classify these neighborhoods from green, which means they will definitely pay back a loan. You should give everyone here a loan. Those historically were white communities, down the yellow and blue colors to red, which means no one in that community was offered loans. So on the left, so that's all shown on the right. On the left is the same shape, so we call these polygons in spatial analysis, but now the color is just in the outline and they're overlaid or shaded in by this estimate, what's over here, of air quality. So this is some aggregate score of air quality, this CalEnviroscreen air quality score. And you can see here, so Los Angeles has mountains up here and those also kind of govern air quality, as well as the ocean down here. But you can see that especially in the center of the city, the downtown area, which was historically redlined, also has some of the worst air pollution. And then these wealthier neighborhoods up in the hills, which are outlined in green, also have much better air quality. And I will let you explore this later if you're curious, but you can go down through all of these different forms of pollution, solid waste, hazardous waste, are the cleanup sites there, which is the site where there was like a toxic waste spill or something. But so let's just pick pesticides, for example, and see what the relationship is here. So it looks like all of Southern California doesn't have much pesticide pollution, which means that there isn't really a inequity dimension here. If we go to particulate matter that's 2.5 nanometers or smaller, which is the most dangerous for your respiratory health, this is something that causes asthma in children and reduced cognitive capacity often. You see this effect where it's not great anywhere in Los Angeles, which is a city known for bad air quality, but it's really bad in downtown Los Angeles where, again, there's this history of redlining. So this entire thing was produced in R from start to finish, and the code is here, designed by this person, David Altare. And the Shiny app, So as you can see, there's quite a lot of code in this repository. There's some explanation of how to navigate it here. And I'm not going to spend a lot of time showing you these people's code repositories because it's just not a great way for you to digest it. But I will just briefly say this is, I think, the script that actually implements the app that we saw, the Redline mapping app. And you can see that the first package they call is Shiny, this interactive mapping package. And then they have all of the backend code to create, for example, this interactive drop-down menus that we just looked at where you select which pollution form you're going to map and so on. So I really like that example. The next one is not a spatial one. It's by a collaborator of mine doing a really complicated statistical model to understand how much marine protected areas, which are like marine parks, it's an area in the ocean that the government says can't have most intensive human uses. So you can't go fishing there, you can't develop oil there, you can't drive container ships through it. And the goal of it is both to promote tourism and recreation and also to allow biodiversity to flourish within the marine protected area. So this study was asking how much they really work, how much they really increase the number of fish in the oceans or other species. And what's really cool about this, as scientists, the way we do and publicize our research is through scientific journal articles, which are like magazine articles, essentially, and they're published in a research equivalent of magazines, but they're peer reviewed and they have a very particular structure. There's an introduction, a method section, a results section, discussion, and they often have a lot of graphs, charts, tables in them. Almost everyone makes them in Microsoft Word in my field, so they make the figures in R, but then they like kind of update all of the statistics and figures in something like Microsoft Word, which is kind of breaks the chain of reproducibility, because if you update a statistic in R and forgot to copy paste into Word, your paper is wrong. My nightmare. And this person actually wrote the entire manuscript as an R Markdown output, which is difficult to do because these manuscripts have such particular formatting. So I'll show you what the manuscript looks like first, and it's a preprint, so it's been, I think it's been accepted to be published somewhere, but they haven't actually put out the formatted version. But let's just look at it briefly, and you can see how nice the formatting is. So everything about this was specified from R Markdown, and it looks really nice and professional. It has, I think, some equations in it and tables, and we'll also scroll down and see the figures, which I think are especially exciting. So these equations were created in R, and where there are specific values here, 31%, 3%, those are auto-populated by R when the analysis is run. And if we go to the end where the figures are, this is the model output that, again, is automatically generated from the plotting code when you run the model. I don't recommend hitting run on the script because I think it will take days. This is a very complicated hierarchical Bayesian model, but we'll go look at the script briefly. The entire paper is in this one script, make pop effects of MPAs. I'm not actually going to scroll down far enough because I think it's thousands of lines of code, but if you were to scroll down far enough, you would see the actual text of the manuscript that I just showed you after the entire analysis happened. So it's all in here. And then I assume that it pulls from some other source scripts that do some of the modeling. And I think what they found, by the way, is that the effects of these protected areas in a region that already has sustainable fishing and other kind of sustainable regulations in place were not as large as people thought they would be. This third one is one I put in here because it's such a great example of transparency and data visualization. It's a visualization of something called the Ocean Health Index, which was a project to quantify, to give every ocean in the world a score, a grade on its ocean health. And the grade incorporates everything from how well biodiversity is doing in this region to how many jobs are provisioned to communities by the oceans to how much food is being provided to people from the oceans. Again, the entire thing is done, this is another Shiny app, so the whole thing is done in Shiny, and I think it looks really cool. So the landing page is the overall score for this region, which is the northeastern United States ocean region. And this is called a petal plot, like a flower. it shows you the different scores for the different component scores that get averaged out to 83, which is how well the Northeast US is doing, how well its oceans are doing. And these scores are in categories: habitat, services, food provision, and they're also visualized here as these blocks. So you can see they're doing really well at livelihoods and economies. They got a 99 on this question of how many jobs and how much money are you getting from your marine resources sustainably. But they did pretty badly on how many people they're feeding or where the food is going, and giving people access to the resource, which I think means, you know, how easily you or I could go get up to the beach or could go fishing if we wanted to. And then you can go through the side menu and look more deeply. So of course I'm interested in biodiversity, so I'll go there first and look at the scores for the different habitats. And here you can see actually that they did these scores separately for different parts of the region and then added them together. So that's what this is showing you, these different regions. And you can also see a time series of those scores and look at how they changed with time. So I think this is just a great way to take a super complicated project and let people actually see everything that went in it and how the different pieces stacked up together to get to the final product. And there's a lot more here. These key messages I think are cool. And again, the whole thing's written in R and the whole analysis is done in R. The code for this one is here. And I don't actually remember which of these scripts implements the Shiny app, but similarly, I think the analysis is distributed among a lot of these scripts. But if you wanted to reproduce the website that I just showed you, you could do the whole thing from here. And my last example is a little different because it's not a Shiny app, but I think it underscores one of the other big strengths of using R for environmental work, which is how easy R makes it to access the data that you need to answer your questions. This is a portal from Rutgers, where I work now, that allows you to access the marine biodiversity survey data that I use in my work. So this is the repository where the data are collated and organized and plotted in the interactive plots we're about to see. And then if we go to the website, you can pick a region. So let's look at the Northeastern US again. It zooms in, and now you can pick whether you want to look at changes in the fall or the spring, because those are the two surveys that are operated. So let's try spring. And now you can pick a species. I'm going to pick Atlantic cod, which is a very important species on both sides of the Atlantic, yours and mine. And now it gives you a visualization of the spatial distribution of cod in this region based on the survey data. So the red colors mean there are more cod, blue colors mean there's less cod. And you could drag this to look at it in any particular year, or you can actually just hit play and it will show you the change in distribution over time. So what you see with cod is that it really kind of dies out in the southern part of its range over time. It gets very concentrated up here, which is a deeper, colder part of the ocean, because this area has become too warm for it since the survey started. So what I love about this is, again, it takes something that, you know, this is hundreds to thousands of lines of code to get the data, organize it in the way that you need it to, map it in this way, design the map the multiple year interface that we're looking at, incorporate this play button, and yet you can do this whole thing such that anyone has really easy access to this data that matters to all of us about how things on the planet are doing, in this case like cod, which by the way is not doing great on this side of the Atlantic. So that's my last example of how environmental scientists are using R. I think our next thing to do is for you to try it. And before we get to the demo, there are a couple things I wanted to say. The first is just that the demo requires a lot of spatial stuff, because the demo I chose is spatial. Since spatial data analysis is such a huge part of environmental work, everything that we do happens over some spatial area, and we often have to take that into account. But learning spatial stuff is a whole other topic that we won't cover today. So I've come up with some creative ways for you to access spatial data without having to really wrangle it, and hopefully they work on your computers. And then before we get to the demo, I just want to underscore that hopefully you explore this stuff further. I've put a link here to all of the data access portals from R Open Sci, which many of you are probably aware of. It's a R nonprofit organization that does a lot of package development, and one of the realms in which they develop packages is data access. These are all really high quality packages that give you access to data sets on many topics, but a lot of them are environmental. I use this one a lot. This is a database of biodiversity records, or Gdis, but you could also use ones that have nothing to do with biodiversity, like R-Tweet. But you can see in here, there's weather data from Iowa. There's pathology data in here. There are dozens, I think probably hundreds of these packages developed by R Open Sci. And if you were, after this tutorial, looking for a better or more comprehensive source of data about the climate, about the environment, this is where I'd start. Looking at R Open Sci and seeing what packages they've developed to help people like you easily access data about our planet. But if you do, be a little careful. Like I said, there is a lot of important domain knowledge about all of these data sets. So if you are curious about going deeper down this path, I really encourage you to engage with the environmental community. Like the art community, we're really friendly and always excited when people want to tackle the stuff that we think about every day. So you're always welcome to reach out to me or to anyone else in this community on Twitter and say, for fun, for Tidy Tuesday, made this map of air pollution and I don't really understand something about it. Can you talk to me about it? With that, and before we hop into the demo, I do just want to put up my thank you slide for a second because I have a feeling after the demo, people might start to hop off. I've listed here again all of the people who wrote the code that I just showed you, who clearly did an enormous amount of work on their own parts to design these things that are now open access for all of us. So they deserve a lot of thanks, and it'll be in the slides if you don't get it this second, but this is how you can reach me. If you have any questions after this, you're always welcome to reach out. And the slides were made with Sharingan and Sharingan Themer. So with that, let's switch to the demo. This you can find in the repository. It's called demo.rmd. I think it's also in the one that R Ladies Amsterdam forked and shared with you. I'm going to stop sharing my screen for 1 second and go over to RStudio. I just don't want you to see my whole desktop, which is why I'm going to stop. And then we can start running code together. I saw there are a couple of questions. Is this the right time to answer those, or should I save those for after the demo?
I was going to suggest it might be a good time to just answer the questions now, and then at the same time, people can start shifting to working on the demo.
Okay, awesome. So let me start. I agree that Shiny is awesome. About the historical data on cod, this is something I would love to talk to you about for the next 30 minutes. I'm guessing you didn't want that long of a response. So the short answer is that many federal governments with a history of industrial fishing, which includes all European nations, North American nations, have federal agencies that have gone out every year and gone fishing, recorded what they caught, and made that data public so that they and anyone else who's interested can analyze what trends in marine populations. And this is actually the data I use in my work because I'm interested in how the distributions of species are shifting as a response to warming. And we always joke that counting fish is like counting trees, except they're invisible and they move. We really don't have any idea where they are, except for these surveys. So these wonderful people working for Canada, for the United States, for European fishing nations, and their agencies record what they find on these surveys and often make it public. You also can reconstruct some of what's happened from the fishing industry itself, like what they have caught and how much, but that's much more complicated for a number of reasons that you're welcome to ask about later. So that's the most standardized way that we have to survey populations throughout time. I wouldn't say it's highly accurate because it only happens once or twice a year. And of course they move a lot during the year. Unfortunately, they can swim. And they're large extent and high resolution for what they are, but that still means the points where they go fishing can be 50 kilometers apart, and there can be a lot of change among those. On land, there are a lot better data sets for these long-term questions. And now there are also satellite data sets of things like tree cover, which are really fun to analyze. But in the oceans, we're kind of still tied to these fishing surveys. Oh, someone asked how much am I looking at tracking of individual fish or animal species? So like literally one fish. That is a whole other realm of work, which I haven't done personally, but is super useful. It's especially useful for things that we don't catch often or don't want to catch often, like that are, and they're usually things that are very big and very slow to grow. People put a lot of tags on sharks, for example. So you put it in the shark swims around for a while. Eventually the tag like detaches and floats to the surface, and then you have to go find it. And then in the tag will be a record of everywhere that the animal was. And sometimes it also has instrumentation readings, so like temperature or pressure where it was, that tells you the depth, which is really cool. But it's a very work-intensive approach. And so for things that we can go out and just catch in a fishing net, things that don't live that long, which is most species caught in commercial fishing, we rely more on these large-scale surveys where you just drag a net through the ocean and see what's in there. But for things that are slow to live, things that migrate a lot, they also put tags on tunas because they live for a long time. They crisscross the whole ocean. And we didn't really understand with tunas how much the whole population in the Eastern Pacific or on the Western Pacific were connected versus separate, which is really important because if they're separate, then if one of them collapses, the other one should be okay. Like if one of them is massively overfished, the other one should be okay. But if they have a lot of exchange, then one side of the Pacific could just eat all of them. So we needed to know how much they went back and forth. So people put these tags on tunas, and I think they do go back and forth a lot actually. But it's a challenging way to do research. So it's not used that extensively for things that you could just easily go out and catch. So I'm gonna share my screen and we'll see how we do with the demo. I saw someone put a message in here about an error, which I think I'll probably talk about when we get there if it's still there. And it sounds like not everyone's having that problem. So it is on line 68. So we'll talk about it when we get to line 68. Is this big enough? Can you all see the code okay?
Yep.
Okay, I'm seeing nods.
Yep.
I'm just gonna save this and refresh my R just to be sure I don't have anything loaded. So many of you have probably seen R Markdown before, which is what this is written in. If you haven't, each of these gray highlighted boxes is a chunk of code that we're just gonna run one at a time. This one just sets options for all of the chunks, saying not to give too many messages from them because it's just annoying. The goal of this tutorial is to give you a chance to actually get, wrangle, and then visualize some data about climate in R. And we're gonna use data on extreme high temperatures over land in Europe from packages developed by someone who's done some really cool package development that makes it really easy to get these spatial data sets without actually having to do any of the gnarly work to import them into R. So thank you to Mike for creating these things. And again, don't worry if any of this is unfamiliar, the spatial part, the tidyverse part. You should be able to hit run and follow along, and then you're welcome at the end to let us know what didn't make sense. I'm gonna skip the package installation because these are all installed, but this is where you should start if these aren't all installed. These are the kind of special packages that are just for today, and then these are really widely used data packages, the first two for tidy data manipulation and the second two for spatial stuff. All right, so I'm gonna start running things. Let's load the packages. Okay, that worked well, great. The reason I'm doing this, by the way, is just because there's also a function in Raster called select, which I don't want to use. So I'm just telling it, if I write select, I mean the version of select from dplyr. So the first thing that we'll do is get our country of interest. The one I'm going to do is the Netherlands, but you can pick any country, so you're welcome to edit it. And we're going to use this special function from these packages that I'm using today that will get an area of interest, which here means a polygon, so an outline of something that roughly is an outline of the country. It's going to be very rough because we don't really care about the exact country borders, and the higher resolution stuff is in the spatial world, the longer it takes. And if we look at this thing that we've just created, Aoi, you'll see that it has this weird structure where it's a data frame, which should be familiar to many of you. So it has data in it in a normal tabular format, but it's also something that's called SF. which means simple features. And by the way, I'm not gonna fully follow the chat because it's kind of hard for me to go back and forth, but if one of the organizers can just shout if there's something that I should stop and talk about, I would really appreciate it.
Yeah, we're just, it's all, anything on the chat, we're taking care of it. It's mainly like specific tech questions, so.
Thank you so much. Yeah, and I'm happy to, if there's anything more generic, let me know, and I'm happy to pause and explain.
Yeah, we'll definitely let you know.
Thanks. So the other thing that this AOI object is something called SF, which stands for simple features, and it is right now the predominant way that people do spatial analysis in R. It's an R package, and it's also kind of a way of thinking about spatial objects, which is a little different than the way people thought about them before. I won't get very far into it, but suffice it to say what's cool about it is that any spatial object can be an SF, which didn't used to be true. There used to be many, many classes of different spatial objects. And so this makes it much easier to do data analysis on something and keep it spatial. Whereas it used to be that if you wanted to, for example, look at average rainfall over an area, you'd have to kind of remove the spatial elements. So you just had the rainfall, average it, and then reattach it to the spatial dimensions. We don't really have to do that anymore, which is awesome. I told you this was a polygon of the Netherlands. So let's see if that's actually true and plot this polygon of the Netherlands. Kind of looks like a tooth because it's a very low resolution outline, but I will believe that it is a low resolution outline of the right place. And like I said, it's a polygon, so it's an outline. It's not like a filled in spatial object. I also should probably check that it is in the right part of the world. They have a different function for this in this AOI package called the Aoi Map that automatically will put your area of interest onto a Google Map looking thing, basically. So let's run this. Ooh, that's fun. It did not do that earlier. Let's see. Try running it again. That's interesting. I wonder if it'll, let me try knitting this to an HTML and see if it'll work.
Also the line we're debating in the chat, that's broken.
Ah, you also had this error.
Yeah, it's a different error, but the same line.
Oh, interesting. It didn't happen to me this morning. But would it really be a tutorial without something going wrong? Sorry.
No.
Maybe the projection needs to be changed, or maybe hard.
Yeah, that's certainly what it's hinting at. But I don't know why it is only upset about it now and wasn't earlier. So let's see if it doesn't work. I'll probably just proceed and see if we can get the rest of the code to run without it, because this is just a check to show you where in the world the area of interest is, which we know is in fact the Netherlands, but mine is very slowly trying to actually turn it into an HTML, and we'll see if that works. But let's try.
On my end, I was actually able to do it, so maybe some other participants have been able to actually run it without an error.
Are other people stuck on this line? Let's see.
So some other people, for them it worked. For someone, the screen flipped upside down. I don't know what this means.
Oh no. So if you do, one thing that can be annoying about this in R Markdown is that if you're scrolling up and down through R Markdown, it will zoom in and out of the interactive map that's kind of embedded. So if that is what's happening to you, you can just press these upper arrows here to hide it. And sometimes that helps. But I would say let's keep going and see if we can get the later code to work, because that's not essential. And if we can't, then we'll stop and debug together. The thing that I really want you to do with this AOI object, and we'll see if it works, is to use it to fetch temperature data. So a big part of spatial analysis is kind of intersecting a large gridded data set like temperature around the entire planet with your area that you want to work on, which here is the Netherlands. So what we're trying to do here is use a function specific to now the climate R package called getTerraClim that will access a particular data set called TerraClim and pull down from a server data in this area of interest from this start date to this start date, and for a variable that we've defined. The variable that I chose is maximum temperature. I think it's maximum daily temperature. in a particular area over a year, I want to say. But you could look at it and pick a different one if you want to. The way you would do that just for these packages is to run this line that's commented out, param meta $terraclimb, which I'll run so that you can see. It shows you all of these different data types that you could fetch if you want to, and what each of them is. So the common name and what you would call. So I'm doing Tmax because it's kind of an intuitive one. But you could certainly do something like wind speed or soil moisture if you wanted to. So let me run this chunk and see if it'll run. Oh, it's doing the same error. Okay, so strange. Has anyone else managed to fix it?
Yeah, I was able to. I wonder maybe the AOI needs to be redefined at the top.
Ah, let's try that.
But I don't know if it's associated with the run.
Huh. Well, so mine worked on when I rendered it as an HTML.
Oh, okay.
Which is weird. So I might just switch to showing you that.
Yeah.
And I apologize that I picked something that I think these packages are just kind of buggy because they're sort of custom packages that are just for these specific purposes. So I will switch to that and hope that at least some of you can follow along. Sorry about that. I'm gonna share this window instead. So actually, I'll just share my whole screen so that we can kind of go back and forth. Desktop too. Here we go. So this is our markdown window that we were just in that isn't working very well. But I hit knit to HTML and it does work when I do that. So you're also welcome to try doing that. It will take a minute to run through the whole thing, but we can at least kind of go between the two and look at what it should do if it works. Yeah. So earlier when I said it would generate this interactive map to show you where the data is actually coming from, here's the interactive map. And like I said, very crude outline, but it is in the right place. And you can zoom in and out to confirm you're in the right part of the world if you didn't know already. And now we'll pull in the temperature data from TerraClimb. Like I said, I'm looking at Tmax, although you can choose any variable that you like. So we're in the code, we're now down here. And I pulled it, I think, from 1980 to 2015. If you look at this object, which I guess I can't do because it's not in my environment, but if you do something like class.raster, like I said, I'm not going to run it because I don't have it, but if yours worked, you can explore. You'll see that it is a list object, and inside the list is one thing which is called a raster stack. You really don't need to worry about what that is. It's a type of spatial object, but it's a set of consistent layers, which you can think of as maps of a particular thing that are stacked on top of each other because they're replicated in some way, usually, and in this case, over time. So the first thing that we do with this stack is we get it into this SF format, which I was explaining is much easier to analyze. And this is just kind of some wizardry to do that. You have to go through this intermediate step before you can run this function, which transforms it into a SF object, and then we make it tidy and do a bunch of other wrangling to fix the format of the date, which we really need because we're looking at temperature over time, and the way the date format comes out of these raster objects can be kind of weird. And now if we look at this, it's going to say, once again, that it is a data frame, but also an SF object. And we're just confirming here that the date is a date and that it looks normal when we look at the first few dates, which do look normal. If you haven't dealt with date formatting, I envy you, but it's a huge headache. That's why we loaded this package called Blooper Date earlier. And that's really what this chunk of code accomplishes. So now that we have a spatial thing that's also a data frame that contains the following information, the geometries, like where the data are from, the date and the temperature, let's look at temperature over time, which is kind of a natural first plot to make when you're exploring this. That is what this is. I didn't do any formatting of these plots. Many of you are probably ggplot wizards who could make really nice ones, but I just was doing this to show you the kind of exploratory first analysis I might do. And mostly what you see here is the signature of the seasons, right? These are maximum temperatures, which I think are daily values. They might be monthly, but either way, you mostly just see that in between each year, they go up and go down, go up and go down, representing the season. So this is not a great way to look at change in temperature, if that's what you're interested in. So instead, let's for every year ask what the single greatest temperature was, like everywhere. So one temperature value for the entire country per year from one place where temperature was recorded. In fact, this is a high resolution data set. So I don't exactly know how many points there will be in the Netherlands, but it's a lot, like hundreds. And here we're just saying, what's the hottest one every year? And so this was the code for that first plot. And now we're just doing some grouping and summarizing to get it to a single value per year. And the plot still looks very messy, but it's a little bit easier to interpret. So really what you can see is there are some years where you just have these incredibly high temperatures. And then otherwise high temperatures are kind of around the same value, which makes sense just from the warmest days in summer. But one of the things that we might ask, because this is a climate topic, is have temperatures gone up over time from warming? And you can fit a line to this plot to ask that question sort of statistically. The way you do that is pretty straightforward. It's just this geom smooth function, and method equals LM means linear model, which means fit a line. So here's the line, but this is a weird way, and it does look like it's gone up, but this is a weird way to think about warming because we just picked one value for the whole year. And it's probably better to look at the maximum temperature at every point in the Netherlands every year, not just the one highest point in the Netherlands every year. So if we, rather than have one point every year, have as many points as we had samples, which is what this plotting code does. So we're not grouping by as many variables anymore. And now we're using geom point to get a dot plot instead of geom line. It looks like this. This is all of the different maximum temperatures around the country for a year. And the line, you can't totally see this, but the slope of the line is a little bit steeper because it's not as affected by kind of the weird way that we were thinking about maximum temperature in the previous plots. This is probably a better way to think about maximum temperature. And just to check if it is actually warming, we can do some statistics on that line and just fit a very simple linear model to it, which is the same thing as the blue line in the plot. We're now just kind of examining it from a statistical standpoint and ask if we have a linear model where we're asking how much variation in temperature is explained by year, how much variation in Y is explained by X. This is the summary of that model. For people who haven't seen this before, the key things here are this value, which is the slope of the line. So this says that for every 1 year, temperature is going up basically 0.05 degrees, which is actually enormous. That's a pretty rapid rate of warming. Of course, this isn't the precise rate for the Netherlands because we didn't do a very thorough way of thinking about temperature, but that's still a really substantial effect size. And we can also ask statistically the probability of this effect being real. And here the probability is basically 100% probability of it not being real is basically 0. And that's what this P statistic is telling you. So we haven't actually made any maps yet, although we've been looking at trends in temperatures. So the last thing in here is to make a map of these extreme temperatures over time. And for that, we will still stay in ggplot land. One of the really useful things about SF is that there's a great interface with ggplot where you can just add spatial objects to a plot the same way that you would add points to a plot. You can combine them, and it makes it really easy to make nice maps. This map, I made a slight effort to make it readable because otherwise it would just be really hard to read, but I took maximum temperatures at every point over the Netherlands over the most recent 10 years. And here's how that looks. The reason these colored parts are square is because the temperature function is actually getting temperature data from a rectangle drawn around your area of interest. So it's not the exact area of interest, but it cut out the oceans, which is good. It only has land data. And actually what you see here is that the 2006 was really hot. That clearly was like a year with a heat wave. You can also see there's some spatial differences in the parts of the country that are inland being slightly warmer, parts of the country near the coast being slightly hotter. And then after 2006, it does look like, you know, there might have been a slight warming trend, but you actually can't see it as clearly from this as you could see from looking at the average over all time. And that does sometimes happen when you take a smaller number of years, which I just did here so that we weren't looking at 30 maps. You don't see trends as clearly. But the to-dos at the end that you can explore, if you want to, are to come up with different ways to think about this data, to try a different variable, to look at different years, change the analysis. Maybe you're trying to specifically pick out heat wave years and map those rather than just look at a particular decade. Or change the country and the variable entirely and see how the visualizations look and if you need to adjust them. So I will pause there. I really hope that at least some people got the code working, and I'm sorry about the weird error that cropped up. Let me tune back into the chat, and in the meantime, if there are any questions, just let me know.
Thank you. I think for most people it now worked. At least I don't see anyone that didn't get it to work right now.
Awesome.
Yeah, no, it works also on my end, but I did want to mention the dat_SF object. So the moment in which there's the wrangling with the dates, it does take quite a while, and so I wanted to highlight that. That's
Thank you for saying that. So this, one of the difficult things about spatial stuff is just that it's very memory intensive and computing power intensive, and anything where you are joining or manipulating or cropping the spatial object can take a very long time. So sorry if that took a while on your computers, and that is something to think about as you proceed with spatial analyses. In a lot of my analyses, I end up kind of cropping a global gridded data set like temperature to an area of interest, just the way we did. And I usually like hit run on it in the morning and then come back at night to get the data out. It is slow.
Yeah, no, it is an important thing to note about spatial mapping on
MR.
It is really heavy.
Yes, it really is. And actually sometimes the tidy solutions for spatial stuff, which I've showed you, are not actually the fastest ones. Mm-hmm. So I often actually use some of these older tools for spatial analysis, which are clunkier to code, but can run a little faster. So I still use the Raster package a lot for gridded climate data, for example. Let me. So slower than an ArcGIS, I think really depends on the operation you want to do. I haven't used ArcGIS in a long time. I suspect there are things at which ArcGIS is faster. But I think there also are a lot of things for which R is faster. It depends on exactly the operation. That's not a super helpful answer, sorry. Someone else asked if I have access to a bigger machine. I do, which is very lucky. So I have access to a number of computing clusters at Rutgers that I can use and abuse pretty easily for free, which is really great. But the nice thing about spatial stuff, as opposed to some of my other work like statistical modeling, is it won't crash your computer. It might just take a long time. Spatial analysis, though, is a great example of something that you should develop on a small data set. So a mistake I've made many times is downloading 50 years of climate data and then figuring out what to do with it. And what I should have done is downloaded 1 year of climate data, figured out exactly what to do with it, and then rerun it with the 50 years. So it is a good chance to revisit your workflows and ask whether you can kind of develop your methods in a more streamlined way and then reapply them to a bigger problem, which other languages force you to do that don't let you run code line by line. Like Python users think this way, I think, more automatically because you just execute a whole script at once. So it would be kind of natural to execute the script on a smaller data set and then re-execute it on a bigger one. But in R, because we run things line by line, I at least often fall into this trap of just building up and up and up, and then things get really slow, when in fact, you can be a little bit smarter about the way you construct these really time-consuming scripts. I'm really glad the code ran for you, Marty. Thanks.
Yeah, I guess I might as well just add that it's a really good point about you can always build something quite complex, and then it's that point when you're cleaning it that you make it a little bit simplified and more efficient as well. So it's kind of part of the process of like expanding it and maybe building upon the script and then tidying it at the end and then sharing it potentially at that stage.
Yeah, and again,
with
generating these maps, for example, often it can take a long time for ggplot to render a map also, because they can get, if it's a high resolution map, it can take a long time. So if I were actually making this map for publication, I probably would just pick 1 year and make a really pretty map, and then at the very end do the one where it plots every year, so that it doesn't take me forever to develop every time.
Yeah.
Someone asked how much I need to know about geospatial data. I feel like I have an intermediate level of knowledge about geospatial data. I've taken a class on GIS a long time ago, but I end up just Googling everything every time, because geospatial data is one of these branches of computing with just so many variable types, so many different histories of package development. So they're kind of different generations of using this data, so many contingencies. Like there is a special file format just for climate data called a netcdf, like .nc, and it's its whole own file, doesn't exist anywhere else, doesn't get used by anybody else. So I would say I'm competent enough to Google and find the right answer about these things at this point. I wouldn't be able to pull it out of my back pocket without doing that. And I think that's probably true of most people who do spatial analysis, unless you are like a full-time spatial software developer, that it's just a complicated toolkit. But that said, there are some spatial tutorials that if you follow them through, you would have probably been able to come up with this tutorial I wrote, for example. Do something like get data, crop it to an extent, visualize it or analyze it or get the data out and do some statistics with them. So that I think is not too high of a bar. I think that's a reasonable thing for many of you to learn to do if you're interested. In terms of the next question was, what are the most common analyses that people do with climate data? And usually what we are doing is looking at trends over time. The question is always how you aggregate the data, and this is where having transparent code is so important. Someone might say, oh, I looked at monthly temperature over time, which sounds like it is one thing. But as we just saw, you could ask, did you average over a month for a whole country? Did you average daily data for a whole month in every pixel in the country and then take an average of that? Did you look at extreme temperatures every month and then pick a particular set? So often, if you're just trying to communicate things about climate change, you often look at kind of straightforward averages, like changes in average temperature over time, or changes in average maximum temperature over time. For the stuff that I do, you can get much more precise, trying to understand how temperature relates to biology. So I've looked a lot at reconstructing exactly what temperatures were there when a species was found at a particular time. So, you know, if the survey was done on June 10th, 1992, what were the oceans like on June 10th, 1992 for every fish where we found it? And those are more complicated data wrangling tasks because you have to kind of match those things. But I think the most common things that people do with this climate data is look at trends over time. There's something else I was going to say on that topic and I can't remember. Yeah, I'll pause there. Okay, so I've tried to predict extreme events. We can predict, so that's a great question. Extreme events in the world of the environment and climate are things like hurricanes and heat waves. They also, things like tornadoes and earthquakes, we can't really predict at all. Actually, tornadoes are partly predictable. Sorry, my partner left his phone here and it's ringing, so we'll just ignore that. But a lot of extreme events are really directly linked to temperature. Like, we know what causes hurricanes to form. It's particular patterns in the atmosphere of wind, water vapor, temperature that coalesce and create something like a hurricane. We can identify trends in those drivers, like the water content of the atmosphere, like temperature in the atmosphere, and we can identify how those relate to the frequency of hurricanes. So we can forecast the frequency of a lot of temperature-mediated extreme events. We can't forecast exactly when they'll happen. And that's just because of basically an initial conditions problem. It's the reason that your weather app on your phone can't tell you the weather more than 10 days in advance. We've been collecting data on weather for decades at incredibly high resolution, and we still can't forecast more than 10 days in advance. And it's just because if you were to slightly change the temperature now in one place on Earth by a millionth of a degree, by the time you get 12 days out, those changes could have propagated to really affect the outcome. So in the short term, if you understand your system well, like we do global climate and weather, you can predict things with very high accuracy. As you go further out, it's harder to predict. But we do still have a very good understanding from atmospheric physics of these trends of how generally temperature, generally features of the atmosphere are going to change, and generally the relationship those have with extreme events. So we can tell you with a reasonable degree of certainty how much more intense hurricanes will be in the future, how much more frequent heat waves will be, but we're almost certainly never going to be able to say there'll be a heat wave on July 30th of 2061. That's close to impossible. And people have been asking about the difficulty of publishing and other challenges in this field. The biggest challenge, I think, in my work is just how many things I have to be good at. My background is not in climate science. My background is in ecology. So in my bachelor's, I studied coral reefs, for example. So both having to have a deep understanding of natural systems, a really strong background in statistics and computational tools, and then also this coding skill, in addition to understanding other fields like climate, like fishing and the fishing industry, which is also kind of its own thing. Having to be on top of all those things at once is a challenge. And of course, if you aren't on top of them, your science won't be as effective or as accurate, which is not what we want. And I don't think it's especially difficult to publish research in this field. I really appreciate the process of peer review that we have, because it puts a quality check on what's produced. There's a huge amount of literature produced in this field as it is. And I think most of it is of good quality, but I generally have had good experiences trying to publish things where people who are my peer reviewers will give me useful, constructive feedback that makes my work better. And then conversely, I've served as a peer reviewer many times, and often I get to read great research and say, this is really awesome, we should publish it. But I sometimes also read research that I think has real problems, and then I think it's useful for that process to say, wait a minute, we shouldn't share this with the public until you've worked through the following issues in your approach or the way you've interpreted your results. So someone asked a great question about learning GIS, so learning spatial analysis through R, which packages to start with, and they named a few. So I think of the packages that you named, there are some key differences that might help understand where to start. So I think the place to start is learning the package SF, which is for just generally handling and analyzing spatial data. Then if you want to focus on visualizing spatial data, you could go into something like ggmap, which is a specialized mapping package, but you actually don't need it. As you saw today, we made this map without using it because ggplot lets you plot SF objects. So I think I would start with SF. They also mentioned a package called rgdal, which is like a backend package for a lot of these things. So you'll probably need to have it installed. I hope you never have to use it directly. And the packages like Leaflet and MapView are more for interactive maps, which is probably not where I would start learning unless that's something you need to produce for your work. Let me see, so I'll stop sharing, and I usually have a long list bookmarked of resources for learning this stuff. So let me see what my spatial list is and see if I can put some links in the chat before we wrap up about spatial stuff. Very long list of resources, but hang
Also,
on.
I think, I mean, I also would add Leaflet. I know a lot of us in R Ladies have come across Leaflet, even besides looking at GIS software, just like more coordinates or points on your in your city. Just open it, do it with Leaflet, and I think that's a good one. And that people
That's such a good point.
Have used.
So what should I say is my favorite way to learn spatial stuff? One sec.
Actually, go ahead. Actually, go ahead.
Oh, sorry. I was just going to say, I can't find a tutorial on SF right at the tips of my fingers, but that is what I would start with is a tutorial for the R package SF. And I'm happy to share some later if you remind me. And then I think from there, it would be clear if you are going to focus more on interactive mapping or on handling really complicated input spatial data sets or in a different direction.
We can easily also follow up with an email to attendees with these bookmarks as well.
Awesome.
Feel free to send those over to us and we'll send it over.
Sarah shared one, which is great. Thank you, Sarah.
I guess I was just going to add a quick comment to the group here. If they had maybe tried to run the script with another geography or another parameter. For those of you who have been successful at running the demo, it's, yeah, as Alexa mentioned, just switching out some of the parameters, for example, some of the like measurement or variables, taking maybe not Tmax, but taking like precipitation and seeing how your map changes. I'd be curious to know if you guys have had any outputs for that. No? I guess not. I didn't as well, but I will try after this session. Just to see what.
Yeah, it does take a while to run, so it's not the easiest thing to update it a million times and see what happens. But let us know what you find.
Yeah.
Super nice, Alexa. Thank you so much for allowing us to scratch the surface of your field of interest. It was really nice to hear you speaking so passionately about the field that you're so active in. So yeah, I'm really happy to be listening again about talking about topics like modeling data and GIS and everything else that I used to do also before joining the Netherlands team. But let me say that in the Netherlands, it's pretty common to actually focus a lot of analysis on the GIS perspective. So many of the tools that we use here have been developed by developers in the Netherlands, and they're pretty commonly used when you want to scale up your approach and add a third dimension, let's call it a spatial dimension. So this country, yeah, it's really a good one to be in and be actively involved in the spatial analysis in general. So for people who are from the Netherlands, yeah, it's a great place to be in.
Thanks for sharing that. That's wonderful to hear, and also exciting that this used to be your area as well. But I'm glad I'm speaking to people who love and appreciate spatial data as much as I do.
Definitely.
Great. So again, this was amazing. Such an awesome talk, and we got to learn so much about like what you do in your research, and also we have now code that we can ourselves play with and take and expand upon. And also, I think what a really great part about your talk was all the resources that you provided in the links, things that we could further investigate. And I think a lot of the people here that have attended really appreciate that as well. I wanted to open it up and see if anybody else had any other questions related to the talk, or also more broadly about R Ladies or the topic of climate change, and anything, comments or concerns. things that may have come up that you've run into that comes to mind. Please share. We're gonna leave it for another 5-10 minutes, but I think I also welcome people. I know it's come to 8 p.m. soon, so you need to leave it. Wrapping up, and feel free to close out too. Anything come to mind? Inspiring thoughts?
Have you also worked with the Gulf Stream data, like the warming of the Gulf Stream and topics related to that, and the fish?
I have not worked on it. So the science of the Gulf Stream itself falls into oceanography, which is another field that I sort of have like a passing understanding of, but usually collaborate with oceanographers rather than trying to do that type of analysis myself. A study just came out about the Gulf Stream saying that they think it is weakening already, which is really interesting. So this actually is really related to this earlier conversation about what is more forecastable and what's less forecastable. So we can forecast with a relatively high degree of certainty what will happen to temperature at the surface of the oceans under different global warming emissions and mitigation scenarios. But translating those predictions into specific things about specific parts of the world, like how will climate change affect a particular ocean current, like the Gulf Stream, is a much bigger statistical lift. But they have, when you kind of run forward a simulation of the global climate system, there have been scenarios under which the Gulf Stream, which is a major current that brings warm water to and other parts of Europe from the tropics via the east coast of the United States, there are some scenarios in which it weakens massively or stops being a current entirely, which would really change the climate in a lot of countries around the world. I think there also are scenarios in which that doesn't happen. So understanding which of those simulations is most likely to be true is kind of still under investigation, but it does seem, one of the funny things about climate stuff and any form of prediction is you gain more data every day as time passes, and what was a forecast becomes a reality that you can use to validate your model. So as these models get stronger and as we get more data, it does seem that the Gulf Stream is weakening, which is not great. It is not what we hoped would happen. Someone just shared a cool interactive article from the Times about a different current and how climate change is affecting its circulation. Someone asked about a good tutorial for NetCDF. NetCDF files are the worst. That is the file format that climate data comes in. But I have some saved somewhere, and if you send me a reminder, I'm happy to share them. That is also something that I should have mentioned earlier when we had more folks on the call, but is still relevant to those of you who are here, is if you use Twitter, you probably are familiar with hashtag #RStats, which is a great way to get the attention of the R community and get them to weigh in on your question. But there's also a hashtag #RSpatial, which is checked by a community of fanatically fabulous spatial developers who have answered a lot of my questions about things like NetCDF files. So my general approach with NetCDF is to get as far as I can in importing those data formats and then often ask for help. So sometimes they end up on Stack Overflow or on Twitter, but I do have, I think, some tutorials that will maybe help you not end up in that place, and I'll happily send them to you later. It's not, I shouldn't be this negative about it because I don't want to scare anyone away from using it. It's just kind of a complicated file format, and the way you access it from a server is it kind of ends up in a place in your computer, and then you have to find the exact path to where your computer stashed it and then pull it into R in a particular way. So it just requires some kind of specific knowledge of how to do that. Folks are heading out for dinner, which I totally understand. There also was a question about the causes and consequences of species range edge shifts in warming oceans, which someone might have known was the title of my PhD dissertation. So the causes of species range edge shifts are temperature plus a number of other processes that include predator-prey interactions, oxygen availability, the species abundance, and just generally how many of them are in the ocean, which affects their ability to move through space. The consequences are, I think, very profound, not just for the species. Some of them will benefit as they shift their ranges in response to warming, but others will suffer either because their historic habitat becomes too warm and they don't have available habitat, or they can't spread very well, like coral species, and they just kind of suffer in place. That's a species level consequence. You can scale those consequences up, and lots of people do, to understand the consequences for food webs and whole ecosystems. What happens if a particular component of a food web starts to decline? And then sadly, they have consequences for people as well. Sometimes range shifts just result in kind of one fish leaving, another fish turning up, and everyone's okay in the end. But they can also cause sort of more wholesale ecological meltdowns if really important species vanish or decline and there's nothing there to take their place.